Swayam Prabha. Digital India. Educated India.
We'll be continuing some more numerical problems. In this lecture, I will be solving a numerical problem based on the condition of refrigerant superheated at the inlet of the compressor. So, a refrigerator uses R134A. We are using the same refrigerant as the working fluid and operates on an ideal vapor compression refrigeration cycle between the temperature limits are evaporator temperature is -18 and the condenser temperature is 32 degrees centigrade. The refrigerant is superheated to -10 degrees centigrade at the inlet of the compressor. If the mass flow of the refrigerant is 0.05 kg per second, determine the rate of heat removal from the refrigerator space and power input to the compressor, rate of heat rejection to the environment and COP of the refrigerator. So, here the condition of the refrigerant is given. The refrigerant is superheated to -10 degrees centigrade at the inlet of the compressor. So, we will be solving the question. We will solve the. So, this is, let me draw the TS diagram first. For any numerical question, we have to plot the temperature entropy diagram as well as the pressure enthalpy diagram. This is TS. Pressure enthalpy chart. So, the refrigerant is superheated at the inlet of the compressor. So, from here to here, that is superheated. Then the compression. So, this is 1 to 2. This is 3, state point 3. This will be heat rejected by the condenser. This is work of compression. Then we have the throttling process followed by evaporation. So, let me draw it again. So, let us take this point as 1 dash, this intersection point 1 dash. This will be 4 and this will be, and let us take this point as 2 dash. So, this is the evaporation process QE. So, if you see this diagram, so similarly we can extend the isothermal lines. That is here T2 dash is equal to T3, which is equal to condenser temperature. This is superheated. T1 dash is equal to T4, which is equal to evaporator temperature. So, this is given as -18 degrees centigrade and this is 32 degrees centigrade. Now, let me write it here. There is one more temperature which is given, that is from 1 dash which is the saturated vapor state. The refrigerant is superheated to a temperature of minus 10 degrees centigrade before it is compressed in the compressor. If you see this is the temperature. T1, that is equal to minus 10 degree centigrade. So let us write the given data. Of course, we can plot the process. So this is 1 to 2 isentropic compression. Then this is 2 dash. This is state point 3. This is 4. This is evaporator heat load, condenser heat load. And this point will be 1 dash. Point will be 1 dash. Okay, this is the diagram. 1 to 2 is the isentropic compression of the refrigerant from superheated condition, and of course the outlet also will be in superheated condition. So let us write the given data, complete the given data. Mass flow of the refrigerant is given. So temperature corresponding to state point 1 is minus 10 degrees centigrade. M dot R is equal to 0.05 kg per second. Evaporator temperature is equal to T1 dash is equal to T4 is equal to minus 18 degrees centigrade. Condenser temperature is equal to T2 is equal T2 dash is equal to T3 equal to 32 degree centigrade. 32 degree centigrade. So let us use the refrigeration table to R134 table to take the properties, and certain things we have to calculate. Certain properties we have to calculate. Now, okay, let us start from state point 1. State point 1, because state point 1 is in superheated condition, whereas 1 dash is in saturated condition. So we need to find out the enthalpy of vapor at state point 1. So first we will find out H1, and it is similar to the formula which I used before. Superheated enthalpy equal to saturated enthalpy plus Cp of vapor into delta T. State 1. So let us find out H1. H1 is equal to, this is the superheated state, this is the saturated enthalpy. So H1 dash plus Cp of vapor into delta T. So this will be equal to H1 dash plus Cp of vapor into delta T is T1 minus T1 dash. T1 minus T1 dash. T1 is given, the refrigerant is heated to a superheated state to a temperature of minus 10. T1 is minus 10. T1 dash is nothing but the evaporator temperature, because 1 dash to 4 is a isothermal line. That is corresponding to evaporator temperature of minus 18. So both the temperatures are known. Since both the temperatures are known, we can find out the Cp of vapor, specific capacity of vapor, for the average of the temperatures of T1 and T1 dash. And H1 dash can be directly taken from the table, which will help us to find out enthalpy at state point 1. So let me write it here. H1 dash is equal to Hg, saturated vapor enthalpy, at minus 18 degrees centigrade. At minus 18 degree, because the temperature at the state point 1 dash is evaporator temperature, which is minus 18 degrees centigrade. from R134A tables. So let us go to the refrigerant tables. So corresponding to minus 18, vapor enthalpy, this is liquid enthalpy, this is vapor enthalpy, 387.89. 387.89. So H1 dash is equal to 387.89 kilojoule per kg. Let us determine the average temperature with which we can find the specific heat capacity value. Okay, let us take the average temperature. Go to the next. T1 plus T1 dash by 2 is equal to T1 is minus 10, T1 dash is minus 18 divided by 2. So this is equal to minus 14 degree centigrade. Cp of vapor should be taken at the average temperature, average of T1 plus T1 dash by 2. That is Cp of vapor should be calculated at minus 14 degree centigrade. Minus 14 degrees. So from tables, this is minus 14. Cp of vapor is, this is specific capacity, last but one column is specific heat capacity of liquid and the last one is Cp of vapor. So 0.827. 0.827 kilojoule per kg Kelvin. Cp of vapor is equal to 0.827 kilojoule per kg Kelvin from R134A table at minus 14 degree. At minus 14 degree. So Cp of vapor is, this is what I have mentioned in the PP. 0.827 kilojoule per kg Kelvin at the average temperature of T1 and T1 dash, which is minus 4. Now we can find out H1. Substitute the values of Cp of vapor, comma. Let us take this equation as equation number 1. H1 dash T1 dash in equation number 1. In equation number 1. H1 is equal to, H1 dash is 387.89. 387.89 plus Cp of vapor is 0.827. 827 into delta T. Delta T is T1 minus T1 dash. T1 is evaporator temperature. Sorry, T1 is minus 10. The refrigerant is superheated to a temperature of minus 10. Minus of, this is T1 minus T1 dash. So minus of minus 18 will become plus 18. So if you calculate H1 is equal to, it will come somewhere else around 394 kilojoule per kg. See, 394.51. H1 is 394.51. 0.51 kilojoule per kg. So 394.51 kilojoule per kg. So we have found the enthalpy at state point 1. Now, if you look at the TS or PV diagram, pH diagram, so this enthalpy we have found. 3 can be easily found. That is the saturated liquid enthalpy corresponding to condenser temperature. So enthalpy at 2 we need to find H2. This is the work of compression. This is the work of. So now we need to find out enthalpy at 2. In order to find the enthalpy at 2, we will be considering the process, isentropic process 1 to 2, isentropic process 1 to 2, where we will use a similar relation which helped us to find out the, like in the previous problem, we found the temperature of the refrigerant at the superheated condition. So I will be using the similar formula. There it is 2 to 2 dash, 2 dash to 2. Here it is 1 dash to 1. So I will be using this formula S1 minus S1 dash is equal to Cp of vapor into ln of T1 by T1 dash. So we know that S1 minus S1 dash is equal to Cp of vapor into ln of T1 by T1 dash. So in this, we can find out S1 dash. Because if you look at the temperature entropy diagram, state point 1 dash is saturated vapor. So directly we can take the saturated vapor entropy value from the table R134A table corresponding to an evaporated temperature of minus 18. So now S1 dash is equal to saturated vapor entropy at T1 dash. T1 dash is nothing but evaporated temperature, which is equal to minus 18 degrees centigrade from R134A table. So therefore, the value of S1 dash is equal to, corresponding to minus 18, saturated vapor entropy. This is liquid and the vapor entropy. So 1.7399. 1.7399. 7399 kilojoule per kg Kelvin. Let us take this as equation number 2. This Cp of vapor to be calculated for the average temperature of T1 and T1 dash. Since we have already calculated and taken the value, Cp value 0.827, so we will be substituting in this equation. Now substitute S1 dash Cp of vapor T1 comma T1 dash in equation 2. Equation 2 is this one. So Cp of vapor is 0.827 kilojoule per kg Kelvin. T1 dash we know, given in the question. S1 dash is this value, saturated vapor entropy corresponding to evaporated temperature. So when we substitute all these things in this equation, so we will get S1 minus S1 dash is 1.7399, which is equal to Cp of vapor. Cp of vapor is 0.827, 0.827 into ln of, as I told in the previous lecture, the temperature, since the temperature is in the ratio, we have to substitute in Kelvin, not in degree centigrade. So T1 is minus 10, so that is 263 divided by, and T2 is, let me write it in first, minus 10 plus 273 and divided by minus 18 plus 273. We will get the value of S1. See here, this is minus 10, that is 263, that is minus 18, 255 Kelvin. So you will get the value of S1 as 1.7643 kilojoule per kg Kelvin. 1.7643 kilojoule per kg Kelvin. Now we know that process 1 to 2 is isentropic process, 1 to 2 is isentropic compression. So we can write S1 is equal to S2. Process 1 to 2 is isentropic compression. Therefore, entropy at 1 is equal to entropy at 2. Entropy at 1 is equal to entropy at 2. So just now we have found entropy at 1, which is 1.7643. So this implies S2 is equal to 1.7643 kilojoule per kg Kelvin. So S1 is equal to S2. And similarly, we can use this formula, the formula which we used, because we don't know the temperature of the refrigerant vapor after the refrigerant is compressed. After the refrigerant is compressed. So here, this temperature is unknown. This temperature is unknown. We don't know the T2 temperature. So this temperature need to be found out. So temperature at superheated condition 2 is not known. I will be using the equation similar to this equation, to find out the temperature T2. Find out the temperature T2. So S2 minus S2 dash is equal to Cp of vapor into ln of T2 divided by T2 dash. T2 by T2 dash. So here T2 is unknown, T2 dash we know, that is T2 dash is equal to T3, which is equal to the condenser temperature. T2 dash is equal to T3, which is the condenser temperature. Now, we need to find out the entropy at state point 2 dash in order to find out the temperature T2. Entropy at state point 2 dash is nothing but saturated vapor entropy corresponding to condenser temperature. Now, S2 dash is equal to saturated vapor entropy corresponding to condenser temperature. Corresponding to T2 dash. T2 dash is nothing but T3, which is equal to Tc, is equal to 32 degrees centigrade from R134A. Let us refer the table. This is 32. Vapor entropy is this one, 1.7142. S2 dash is equal to 1.73. Let me check the value. 1.7142. 7142 kilojoule per kg Kelvin. This is the value of S2 dash. Now we have to substitute this value. Let this be equation number 3. Let this be equation number 3. Substitute the values of S2 dash, Cp of vapor. Cp of vapor, there is Cp of vapor again, we need to find out for the average of T2 and T2 dash. But because T2 is unknown, so we need to find out Cp of vapor corresponding to the temperature T2 dash. So I will stop at this point. So with this, I conclude this lecture. Thank you.